Okay, this week we're going to talk about clouds, precipitation, and with that, weather radar, which is just a way of observing clouds and precipitation. So let's see if we can move on here a second. So, how do clouds form and precipitation form? We talked a lot about moisture now in the last week. So, how the heck out of all this does cloud forms? Well, water vapor is invisible, so you can't see it in the air. So clouds are visible, and there's something that causes them to form. We're going to talk about that. So you look at the very bottom object here. This is like an example of the cloud condensation droplet. When clouds form, this is how they look. Really, really tiny little raindrops. And then they grow into bigger drops, and you'll notice they're about 100 to 1,000 times bigger when they're raindrops than they are as an initial cloud drop. So that is a huge difference in size. So what does that mean? Well, when you have a curved surface, water tends to lose, has a lot more surface area, and it tends to lose the water droplet back into water vapor. So it takes a heck of a lot to make truly reach saturation. We say, oh, we always look at saturation as if it's a flat water surface. Well, unfortunately, in the clouds, it's not. So with that curved shape, you actually need over 300% relative humidity in order to get a cloud droplet. We know that doesn't happen. So what causes this? Well, also, this is also due to the kinetic energy in the droplet and stuff being bounced around with the molecules so that they wind up ejecting back into space. So there is something called hygroscopic nuclei. Their special category in this case is condensation or CN nuclei. What happens is that these nuclei, this little dust particle maybe or salt or whatever, actually creates a solution, a solute effect in these little tiny raindrops. When that happens, it allows the relative humidity to actually be reduced back down to 100% for when the condensation will occur. In other words, if we cleaned up the air perfectly and you had nothing in the air whatsoever, no dust particles, no air particles, it would literally take you 300% relative humidity in order to get a cloud to form. But we do have in the air in the Midwest, a lot of it's dust closer to the ocean, some of it's salt. Both are effective, and both are means of getting the solute effect to work, and you wind up with cloud droplets. Now that we've got a cloud droplets, we have another issue. Guess what? These cloud droplets are real tiny, and they're vibrating a lot with kinetic energy. We've already learned that the freezing level with kinetic energy, the saturation point is a little bit lower. So it becomes really difficult for these cloud droplets to freeze. They don't like to freeze. Again, more condensation, in this case, ice forming nuclei. And again, they're not that different from what you find as far as the types of nuclei they are. But most water droplets don't freeze till they get to about around minus 10 degrees Celsius or minus 5, somewhere in that range. And they only freeze then because they have this ice forming nuclei in them. So you wind up with a lot of supercooled water in clouds. That's why when an airplane flies through it or whatever, icing can form very easily sometimes. And you don't, because all this water that's super cold hits these, becomes flat along the wings, and it moves out there and forms icing along the wings. So this kinetic energy that keeps it from happening can be overcome with these ice condensation nuclei. So what about precipitation? I don't know, we have these nice pretty clouds. Well, ice condensation nuclei literally form snowflakes. Almost all precipitation begins as a snowflake because the air is very cold up there where most of the clouds are. And this snowflake, once it's big enough, gets pulled down by gravity. Oh yeah, the friction of the air is going to try to push it back up. But hopefully it's being pulled enough, moving down towards the earth. Eventually it reaches what is called the terminal velocity. It can't go any faster down, and it isn't being pulled back up, so it reaches a speed at which it's moving constantly towards the ground. Depending on the shape of the object, it can be faster or slower. So there are two basic ways that we wind up forming precipitation in clouds. If the clouds are warm, if most of the cloud temperature is greater than 0 degrees Celsius, we have a bunch of cloud droplets. And what happens is, you can see here, they start hitting each other. And one keeps getting bigger and bigger and gradually hitting other ones and eventually becomes a raindrop and hits the ground. This rarely happens in the United States. It happens more in the tropics. In the summertime, it can happen sometimes. And when you think about it, we know that the warmer the air is, the more moisture the air can hold. So under these situations, and some of the times when you can get the very largest amounts of rainfall. Bergeron-Findeisen effect says, okay, we got this really cold cloud up here, and we've introduced ice crystals into it now. We have part that's ice crystals and part that's water droplets. Well, guess what? The saturation vapor pressure over an ice crystal is lower than that over a water droplet. So think about it, the pressure is moving from the higher pressure over water to the lower pressure over ice. So all this water vapor is being dispersed into the ice crystals. So the ice crystals are growing at the expense of the water droplets. So what eventually happens is you wind up with a bunch of large ice crystals that are your snow that are going to begin to fall out of the sky. And here you can see the process working. That is how we begin. Eventually they're going to come down into a lower layer. They're going to melt probably. Obviously it doesn't snow in the summer. And actually, if you want to know about it, it takes only about 4 degrees above freezing for a layer of 1,000 feet thick to melt a snowflake. So that is something that meteorologists look at to see if there's a warm layer aloft, if it's thick enough to go on to actually melt this snow and make it back in maybe into freezing rain or maybe into all rain. If it's very dry underneath it, you get virga because it literally evaporates back into the air. There are different kinds of precipitation. Rain. The normal one we're talking about, drizzle, is very teeny tiny raindrops. Typically comes out of very low stratus clouds. There are all different kinds of snowflakes. We talk about there never be any two alike. Well, I want you to look at the sizes of them over here on the left. Here's what we call a dendrite. Here's another dendrite down here. They look a lot bigger, don't they, than all the other ones? And that is used in actually forecasting how much snow might fall at your house. The bigger the snowflake, the bigger the amount of snow you could potentially get. If all the snowflakes were more like prisms or pellets, you're going to get maybe an inch. If they had been dendrites, you might get 3 or 4 inches. And that could have significant implications on how your driving is going to be and everything. So we look at what temperatures the atmosphere is, where the main amount of precipitation is forming, to determine what kind of snowflake you're going to get. And here you can see the ice snow forming that goes into water. It may actually go into sleet if there's a thick enough layer below it to refreeze the ice. And if it continues on down where it's not that thick, it may be freezing rain. One of the interesting things about freezing rain, you can see here on this Stuvie diagram that it goes above freezing here. At about 2,000 feet up. So if you were literally driving in the mountains, say in West Virginia, and I've done this in West Virginia, I got caught in an ice storm once where I was in the valley coming into some of the mountain ranges in West Virginia, I knew that if I could get to the top of those mountains, which was like 1,000 feet higher, I probably was going to get into the pure rain. Well, I followed a salt truck up the side of that mountain on the interstate, and we were able to get into that where it literally became just rain, and I was able to move across into the western side of West Virginia, where by then it had become all rain anyway, so I was fine driving the rest of the way in rain. I didn't have to deal with all this freezing rain. Radar. Radar is a means of detecting clouds, precipitation. It can even detect bugs, dust. Radar is magnificent in all the information it can give you. There's a reflectivity mode, which is just that. It is detecting things. And there is velocity mode, which says, hey, where are these objects moving? So here's a look at the radome. You can see there, they're scattered around. There's WSR-88Ds. There's actually 2 of them in Ohio. One is north of Dayton at Wilmington, Ohio, and another one is around Cleveland. There are other radars. Pittsburgh has one. Another one in southern part of in western Indiana. There's about 122 of these around the United States. So Doppler effect is just a shift in frequency that occurs with the radio waves that we send out. And here you can see reflectivity mode shows very intense precipitation. The redder the precipitation, the hotter the color, the more intense precipitation. And here you can see the precipitation moving in we're just showing velocity on this one and not the intensity, but they're moving right next to each other, and we literally can see here is a tropical system coming inland in North Carolina, and you can see the bands of precipitation, and whether this is dual pole, so you actually are detecting what type of precipitation you may have. Dual pole, the only difference from what we used to have with plain old Doppler radar and dual pole is dual pole looks in a vertical direction and a horizontal direction. So we can see shapes of objects. By looking at shapes, I can then tell what type of precipitation it is, and all kinds of things can be inferred from that. Phased array is another type of radar that's out there. It's used by the military on ships. I got to play with it. We have one phased array radar in Norman, Oklahoma that is purely experimental. These things cost literally $1 billion or more per radar, and the Weather Service has never been able to justify purchasing any to put into the field. But they are extremely powerful. They send a lot of information because you're actually sampling the whole cloud instantly. So you can see changes within seconds within the cloud. Whereas a regular radar literally rotates around and you're gradually moving up through the cloud, which it does in about 4 minutes, or you move, and then it starts another cycle. So literally it's every 4 minutes you're sampling the entire cloud with our normal radars. With phased array, it would be every minute or less. Here you can see estimated rainfall, which with dual pole radar is much more accurate than what we used to get. We also are looking at clouds, obviously different cloud types. We have cirrus clouds. Think about it. They're icy, wispy, stratiform, or cumuliform clouds. Interestingly, clouds can form streets. This happens in the wintertime. You're actually seeing here a street of clouds forming, cold air coming across Lake Huron right here. And when it does that, it's getting warmer at the bottom. It's gaining moisture. So what you wind up doing is making that a little bit unstable. So you're developing clouds in the lower level of the atmosphere. Well, guess what? Then it hits Lake Erie and actually gains some more moisture. And then it finally comes in there somewhere, maybe to the east of Cleveland. And you wind up dumping that precipitation, because then you're going to wind up with little hills, helping the air to rise even more. So that's where you get some of the most intense snowfall for example, on your lake effect snows. And finally, advection fog, it can happen over places like Lake Erie. It can happen down here. I had one happen off the Gulf of Mexico when I was at Florida State. All it is fog is forming over the water, and the wind is moving it inland or moving it somewhere. And in the case when I was at Florida State, I was watching a high school football game by campus, and we went from being able to see fine to by halftime, I couldn't see 25 yards across the field. I literally had to walk back to the dorm and hardly could see your way, all due to the fog coming in off the Gulf of Mexico. So I just want one last thing to show you here, a couple minutes. This is an example of dual pole and how it detects your precipitation type. Here is a very intense white, indicates the most intense rainfall or precipitation. And here is dual pole showing the different types of structure of precipitation. And it shows that there's a change in the type of precipitation right in here. This is where the largest hail is falling. This is differential reflectivity. It's a way of looking at how the sizes of the objects around it or shapes compare to each other. When ice or hail is very different shape than this. So it gives you something to look at here. And this, for example, is just the current radar reflectivity down here. And I mentioned in a blog yesterday or discussion that there was a lot of moisture coming in the southern parts of Texas. Well, it's still coming in, and you actually have flash flooding here and here. And if we were to look at 1 hour rainfall accumulation, you can see some of the rainfall in 1 hour is estimating up about 1.5 inches to 2 inches in an hour in some of these storms. Here's another one down in here. So if I'm worried about flash flooding, I want to know where that rainfall is going and if it's continually going over the same area. So hope you get something out of this. Think about now how precipitation is formed and how clouds form. Maybe very different than what you thought. And feel free to ask me any questions you might have.